Now that we know about polar coordinates, and now that we know about a polar plane, we can talk about polar equations. A polar equation is an equation written in the following form: r equals f of theta, where r represents, again, the same as before, the distance from the pole to the point. And this expression right here is going to be an expression in terms of theta. If a point satisfies this equation, imagine that we have a point, let's say a point r comma theta, and we say that this point right here satisfies this equation. What that means is the same as before. It means that when I plug in r over here and when I plug in theta into the expression, the equality is preserved. The left side is going to be equal to the right side. So if a point satisfies the polar equation, that means that when I substitute r and I substitute theta, the equality is preserved. What we are going to do now is to consider the collection of all the points that satisfy the polar equation. Imagine that we start collecting. We start collecting all of these points, all of them, the set of all r comma theta. My goodness, we can have many, many such points. If we collect all of these points right here, now the interesting question is, what will happen if I decide to plot those points on the polar plane? What if I consider my pole, my polar axis, and I start plotting all of those points on the polar plane? Am I going to get a graph? Am I going to get a shape? Am I going to get a curve? So the point of this second video now is to figure out, how do we sketch a polar equation? How do we get a polar equation? We plot points and we try to get a curve. Do we get a curve? What kind of curves can we get from a polar equation? I will go ahead and begin exactly with example 1, and I'm going to give you various polar equations and I'm going to ask you to sketch them so that we start getting a feel for sketching polar equation, or hence polar graphs. How do we do something like this? And what are some of the typical shapes that we can get? They are actually quite fascinating. I am not going to say that they're easy to sketch. You're going to see it's going to get tricky, it's going to get a little bit messy, but at the end, you're going to have beautiful, beautiful shapes. Let's go ahead and start sketching. We're going to start with something that is fairly straightforward. Example 1. It is asking us to sketch the curve that is represented by r equals 4. If you notice, theta doesn't appear. What is important here is that r, the radial length, is equal to 4. That means that theta can be anything. Remember the coordinates of a polar point, r comma theta. So if r is equal to 4, all that is important is that we keep that radial length consistent. So it could be, we could have the point 4 comma pi over 12, or we could have the point 4 comma pi over 6, or we could have the point 4 comma, let's go to the other side, 5 pi divided by 6, or 4 comma 5 pi over 3, and then you can go on forever. So I'm hoping that you're noticing that what is important is for us to keep r consistent. Theta can change. R should always be 4. Let's start plotting some of those points. 4 comma pi over 12. We want to go 1, 2, 3, 4 right here. I'm going to even start with 0, with 0. So 1, 2, 3, 4. So here is my point. Here is the other point. Let's say Let's do pi over 6, 1, 2, 3, 4 right here. Let's do pi over 3, 1, 2, 3, 4. I'm going to be skipping a few angles. And then 1, 2, 3, 4 right here. Then let's do 2 pi over 3, 1, 2, 3, 4. And then let's go to 11 pi over 12. Again, I am skipping a few angles. 1, 2, 3, 4. Let's do pi. 1, 2, 3, 4. And then let's do 7 pi over 6. 1, 2, 3, 4. 1, 2, 3, 4. Hopefully you can start seeing exactly what is happening. 1, 2, 3, 4. And let's do another angle. 1, 2, 3, and 4. Notice how what is happening right here is that I am getting a circle. This simple polar equation is the equation of a circle with radius 4. Because we didn't care about the angle. The angle could have been anything. What was important was to keep R consistent. The same thing would have happened if I would have asked you to sketch R equals 2, for example. R equals 2 describes a circle with radius 2. So it would be exactly 1, 2 right here. It would be this circle right here. If I would have asked you to sketch, let's do that in red, R equals 1, then you would have been sketching this inner circle right here with radius 1. So every single time that you are given a polar equation that consists of R equals a constant and theta doesn't appear, this polar equation is representing a circle. In example 2, they're asking us to sketch the curve that is represented by theta equals 1. Now we have the opposite effect of example 1. In example 1, theta did not appear. Theta was arbitrary, could have been equal to anything. Now in example 2, R is the one that is arbitrary. R can be equal to anything. So let's start building a few points for us to get a feel for the curve represented by this equation. So theta must always be 1. Again, r comma theta is the general form of a polar point. So if r can be anything and theta must be 1, we can have, for instance, the point 0, comma 1, right? 0, comma 1 is precisely the pole because the pole has r that is equal to 0. We could have the point, let's say 1, comma 1. We could have the point 2, comma 1, 3, comma 1. Let's even consider a few negative lengths. I mean, now here, r can be anything, so r can be negative. That means negative 1, comma 1, negative 2, comma 1. We can have negative 3, comma 1. This is good enough, I believe. So I want to make a point over here again that this one is the origin or the pole because r is equal to 0. So the radial length or the radial coordinate is 0. All right. So then if I start sketching this point 0, comma 1, that's going to be the pole. Then we have 1, 1. So theta equals 1 is going to be somewhere. If you don't mind, I will highlight those values. Theta equals 1 radian is going to be between pi over 4 and pi over 3, somewhere there. So what I am going to do here is to draw a ray that is going to go straight here in the middle between pi over 3 and pi over 4 to represent theta equals 1. I will even extend it in the opposite direction because we are going to be sketching negative lengths. Now you can see the ray extending in both directions of the pole, representing theta equals to 1. I'm going to go ahead now and start plotting some of these points. We started with the pole. Now we're going to do 1, 1. So that's going to be somewhere there. Then we're going to have 2, 1 right here, 3, 1 right here, and then we are going to have negative 1, 1. So then this would have been, this point over here would have been 1, 1, but because the length is negative, we go opposite the same amount along that ray. That means, let me do the negative points in green. We're going to be here, negative 1, 1, and then negative 2, 1, negative 3, 1 in this direction. And I think that you get the point now. So what you really notice nicely is that practically we get a line that is going to pass through the pole, is going to match up perfectly with the yellow ray that I had drawn there. So we get a line passing through the pole. Theta equals 1 is a straight line that passes through the point, through the pole. It passes through the origin. So every time that you have a polar equation where r doesn't appear, you have theta equals a constant. Could be 1, could be 2, could be 3 pi over 2. That means that you're going to have a line that is going to pass through the pole. Example 3 is asking us to consider the following polar equation. If you notice, the equation is a little bit more interesting now. Now we see r and we see theta. A is asking us to sketch the curve represented by this equation right here. What kind of curve would that be? And B is asking us to find the Cartesian equation for this curve. So it's pretty much telling us or asking us to take this polar equation and try to convert it into Cartesian form. And I'm going to show you how to do that. It is possible. It should be possible, right? Because we have tools that allow us to go back and forth. So first, let's do A though. Let's try to sketch the polar curve without knowing what it looks in Cartesian form. So how do we sketch a polar curve? I'm going to show you a way that I find very useful and it's very typical in this type of analysis. What I think we should always try to do is to sketch this function in the traditional sense, just as we did with parametric curves, where we think of theta as playing the role of x and we think of r as playing the role of y. So this is in Cartesian form. I will now start analyzing the behavior of r in every segment of my graph. So for example, let's look at this. From 0 to pi over 2, starting with 0, with theta equals 0, I notice that r is at its maximum at 2. But as theta moves towards the right, towards pi over 2, my r's are going to be decreasing in length. I'm going to go ahead and draw rays like this because I want to see it. I want to visualize it. Look at those rays. They are getting shorter and shorter and shorter. And at pi over 2, I have practically no length. R is equal to 0. So I am at the pole in the polar sense. Now, I am going to go ahead and do the same thing from pi over 2 to pi. Remember, I am analyzing in segments. So I'm going to use a different color for that purpose. Let's use pink. Notice now, as I move away from pi over 2, the lengths are starting to pick up momentum, but they're going to be negative. So those rays are getting larger and larger, but negative, just like this. Then I'm going to stop at pi and I'm going to switch colors. Let me use a different color here. Let's say something, let's use blue. Why not? So using blue, now as I move from pi to 3 pi over 2, my rays will now start getting shorter, but still negative. If you notice, they're getting smaller and smaller, but they're still negative. And at 3 pi over 2, I go back to length 0. Now we have one more segment from 3 pi over 2 to 2 pi. When we do that, let's do that in orange. Now the r's are increasing in length. They're getting larger and larger and larger. And at 2 pi, I am at maximum length 2. So again, I'm keeping track of my r's and I'm doing that with different colors. And what we're going to do now is to take that information and transfer it to the polar grid. Now on to sketching. I am going to mainly be using this graph, as I just said a while ago, in the sketching process. We're going to do a rough sketch first. Once we get a feel of the shape that we're dealing with, we're going to go ahead and use these points that I have already calculated here on the table so that we get a more accurate curve. Notice that I picked a few values for theta, I plugged them into the equation, and I calculated r. That's how easy it is. But I only did it for a few thetas because once we start exploring the graph, we'll see exactly the shape that we're dealing with. So I'm going to start by sketching roughly the portion of the graph that is between 0 and pi over 2. I'm going to be following the lengths of my r's. At 0, when theta is 0, we are at maximum length 2. Then, as we move towards pi over 2, those radial lengths are going down, down, and down. And at pi over 2, exactly when theta is equal to pi over 2, r is 0. So we are going to be at the pole. All right, because I did this section in green, I am going to be consistent with my color. So why don't we do this? Let's make this be 1 length and this be 2, r equals 2. So r equals 1, r equals 2. And I'm doing that so that we get a little bit larger sketch. So when theta is equal to 0, we are at full length. And then as we move towards pi over 2, so here is pi over 2. As we move towards pi over 2, those lengths are going to be decreasing. So I'm going to start sketching randomly little rays, but every time, notice how they're getting shorter and shorter and shorter and shorter. And when we get to pi over 2, we are at the pole. So I can already pretty much sketch something like this by joining the tip of those rays, right? So this is what I get, this part right here from 0 to pi over 2. Now we're going to go from pi over 2 to pi. I'm going to do that portion in pink. So let's see what we notice first. We are coming from length 0. We're coming from the pole. And now the lengths are getting a little bit larger. Those rays are getting larger, but they're pointing down. So then that means that r is negative. And at pi, we got a maximum length of 2, actually negative 2. So doing that, let's do that in pink. I will start drawing rays. Now the rays that I am going to draw originally are going to be between pi over 2 and pi. But then we are going to be reflecting them about the pole because remember, we have negative length. I don't want you to be confused first. I am going to start drawing rays in this direction. But then we're going to transition them by doing our little reflection about the pole because r is negative between 0 and pi. So all the rays that are going to be initially here, they're going to be transferred onto this region a little bit later on. So that's my plan. Why don't we start doing that? So we're going to be going from pi over 2 to pi. Let me mark That's going to be 1. This is going to be 2. Same thing over here, 1. And I want to keep track of all that, 1 and 2, and here 1 and 2, just as a guide. Okay, so we're coming from the pole. We're very tiny here. So let's say we start picking momentum. The rays are getting tidy, and I'm just hand waving this. Every time that I draw a ray, it gets a little bit larger and larger and larger, and at pi we are there. So now all of these rays have to end up in the opposite case, in the opposite area. So if we notice, pi over 2 will correspond across to 3 pi over 2, and then we're going to be moving in this direction, in this direction right here, and then pi corresponds to 0, right? If I take this directly across, I'm here. So when I start doing that, I'm going to keep doing that in pink. We're coming from the pole like this, and we are getting larger every single time. Think of this as those reflections. We end up getting something like that. And at pi, we should be at -2. Now, I am going to go ahead. I am going to erase this part. Is this erasing? No, it's not erasing. Now it is. I don't need this part anymore. I already did my reflections. So this is something that I don't need. And if you notice, it's not perfect, but if you notice, if I were to start joining, I end up getting something like this. What happens with blue if I do the section in blue right here from pi to 3 pi over 2? If I do this section, let's analyze the segments. We are starting at -2 again, and then the rays are getting smaller and smaller and smaller. And at 3 pi over 2, we go to 0. So again, from -2 all the way to 0. So I will do that in blue as well. So starting at pi, here is pi, and moving on to 3 pi over 2. So here is 1, here is 2, here is 1, and here is 2. Again, I am going to start sketching the rays as if r is positive, but then we're going to go ahead and reflect them about the origin. So when r is pi, r is equal to -2. Again, I'm going to think though as r being positive. So if it's positive, it's going to go all the way here, right, to 2. And as r moves towards, as we go from pi all the way to 3 pi over 2, those rays are going to start getting shorter and shorter and shorter. And at 3 pi over 2, r is equal to 0. So I am at the pole. That means that we're going to have something like this, getting shorter, 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 shorter every single time, okay, every time, and then 0 there. So now doing the reflection, this ray should go across. That means that the blue ray on the at pi is going to be reflected onto the other side. Look at this ray right here, the second one. That one should go boom directly across. So then I am going to be getting all of these green rays that I already had. So practically then I don't get anything new. I get the top green arc that I had before. Let me go ahead and erase these rays here. I don't need them on the left. So that's what I get. And if I now do the orange part from 3 pi over 2 to 2 pi, the rays now are coming from 0 from the pole, and notice how they're getting larger and larger and larger. Eventually at 2 pi, r is equal to 2. Let's go ahead and mimic that. And I'm going to go ahead and change to orange. So at 3 pi over 2, we are at the pole. And then the rays are getting larger and they're positive. So then that means that they're going to be matching up with the pink rays, just like that. And at 2 pi, boom, we are on the polar axis. So honestly, we never got anything new. We just ended up getting, look at this, I'm going to do it in red now. We ended up getting this shape over and over and over again. And that shape is exactly a circle. It is a circle with radius 1. Let me even locate the center right here. Here is the center. So you can really see that the radius is 1 and the center has polar coordinates of r equals 1 and then theta equals to 0, for instance. But anyways, that's a circle. Even though this is a very rough diagram, notice how we ended up getting a circle. Now, in order to have a more accurate picture, we're going to go ahead and more accurately locate these points so that we can sketch everything nicely, so that we can have a more accurate circle. Here I've sketched already the points ranging from theta equals 0 all the way to pi over 2. You can already see the top part of that circle. So that looks very nice. Now we're going to go ahead and do the negative r's, and I wanted us to do that together. So when theta is equal to 2 pi over 3, let me locate that. So here is 2 pi over 3. R is equal to negative 1. So if R was positive, then R would correspond to 1 and we would be on this part of the ray. But because R is negative, we're going to go directly in the opposite part. So right here, and we're going to locate negative 1. Let's go ahead and do that. So following that, this is going to be right here, negative 1. If you notice, it's directly across this one here. Then continuing now on to 3 pi over 4. And 3 pi over 4, if we do 3 pi over 4, that means that R is going to be approximately negative 1.4. So then here is 3 pi over 4. If R was positive, we would be in this part, but because R is negative, we're going directly across. So negative 1.4 approximately, here is negative 1, here is negative 2, so negative 1.4, let's put it somewhere here. And then negative root 3 is approximately negative 1.7. That happens at 5 pi over 6. Here is 5 pi over 6, but we're going to go in the opposite direction, negative 1.7. So this is negative 1, negative 2, so negative 1.7, let's say somewhere here. And then when theta is pi, if R was positive, we would be 1 and 2, but because R is negative, we're going to go from here in the opposite direction. Let me do that point in red so that matches with this one right here. So now, joining the points carefully, this is what we get. We get the circle, and we were expecting that. Let me go ahead and erase all of these other dots right here. We don't need them. Let's recap on what we just did. We first started sketching by just doing a rough sketch, by just following the motions of these radial lengths. We determined that we had a circle or something that looked like a circle. Then we insisted on accuracy though. We wanted to have an actual accurate curve. So we went and we selected a few values for theta, we calculated R, and you saw how I plotted those points. And indeed, we get a circle. A table is only required whenever you need accuracy, when the problem is asking you to sketch an accurate curve. If the problem only says to sketch, then we don't need points. If we are only sketching, we are only going to do what we did at the beginning. Just follow the radial lengths, transfer that information onto the polar plane, and then trace through the rays to determine a rough shape. Now on to part B. Find a Cartesian equation for this curve. We already know that we got a circle. So whenever we get the Cartesian equation, we should expect to see an equation that determines a circle. So at least we already have that information. So this is how we can start doing that. Let me begin by writing down the actual equation. So R equals 2 times cosine theta. Then we are going to go ahead and multiply both sides by r. So this is going to be my trick right here. When we do that, we're going to have r squared equals to 2r times cosine of theta. Now, we know that one of the equation that allows us to convert is the Pythagorean theorem. So I know that r squared can be replaced with x squared plus y squared. So I'm going to do that. I'm going to write x squared plus y squared. That's going to be equal to 2r times cosine of theta. Now I want you to notice this part right here. I'm going to be highlighting this part. That part, r cosine theta. R cosine theta is x. So I can write this as x squared plus y squared equals to 2x. All this is substituted or replaced with x. So now what I have is the following. Now I have that x squared plus y squared minus 2x is equal to 0. And it's starting to look already like something circular. Notice how we managed to get rid of r and theta. Now this is a Cartesian equation, but I don't yet see a circle exactly. So in order to see a circle, what we are going to do now is we're going to go ahead and complete the square. In order to complete the square, I'm going to get the terms containing x together. So x squared minus 2x, I'm going to leave y squared on the right. And I will complete the square on the terms containing x. So completing the square, that will be x squared minus 2x plus 1 minus 1 plus y squared equals 0. So this over here expands into this when completing the square. And then continuing the process of completing the square, we're going to have x minus 1 squared minus 1 plus y squared. And now we're going to take this negative 1 and shift it onto the other side. So that's going to give us x minus 1 squared plus y squared equals 1. And here it is. This is right now the equation of the circle right there. If you notice nicely, this is an equation with center equals to 1, 0 and radius equals 1. If you forgot how to complete the square, it's not a big deal. This is a process that you can easily try to remember. It's just going back to your notes or searching online or anything and trying to remember how to complete the square. Well, in this case, it was possible to go from a polar equation to a Cartesian equation it may not always be possible, or it may be extremely difficult to do that. So you're going to see in the book that they're not going to be asking you to convert equations back and forth. Most of the time, you will not do this. If you want to sketch, you're going to do just a rough sketch as you saw me doing at the beginning of this problem. I'm going to go ahead and do a few more sketches so that you get the hang of things. In example 4, they're asking us to sketch the following curve. R equals 1 plus sine theta. As I did in example 3, I started by sketching my sinusoid in the traditional sense, where theta is on the horizontal axis and R is on the vertical axis. So here is my sinusoid. To save a little bit of time, I already drew all of the rays representing R, length R, starting from the axis going up to the graph. The graph is divided into the usual sections from 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, 3 pi over 2 to pi, and I stopped at 2 pi because then repetition will take place. All of these graphs are periodic. So after 2 pi, you have exactly the same behavior. On the polar grid, things are going to repeat as well. So there is no point to go beyond 2 pi. We stop at 2 pi. So let's analyze the green section first. When theta is equal to 0, r is 1. So we are starting already with length 1. Then those lengths are getting larger and larger and larger. And exactly when theta is equal to pi over 2, r is twice as much. R is 2. I'm going to mimic that right here in the polar plane. We're going to be going from 0 all the way to pi over 2. So in this case, let's go ahead and do what we did before. 2 marks is going to be 1. This is going to be 2 so that we get a more comfortable sketch. So when theta is equal to 0, we have 1. That means that this is my radial, or that's my ray. Then those rays are going to be larger as I get to pi over 2. And at pi over 2, the ray should be at 2. So let's start doing that. So every time that I draw a new ray, the ray gets larger and larger and larger. So something like this. Remember, this is only a rough sketch, doesn't have to be perfect. So at pi over 2, we are here at 2. So I already see that the shape of this curve is going to be like that. And remember, we started at 1 right here. All right, now let's do this part right here in orange, from pi over 2 to pi. What is so nice about this graph is that we have no negative lengths. All the lengths are going to be positive. That makes things a lot easier. All right, so from 2, we're going to go all the way to 1. So let me mark that first. Here is 1 right here. So as we go from pi over 2 to pi, the lengths of these rays are going to start getting shorter and shorter and shorter all the way to 1. So starting at pi over 2, the ray had length 2, and then it is going to keep getting smaller every time, and even smaller. Let's say in this direction, and smaller, and smaller, smaller, smaller every time until we get to pi. So you kind of notice that you get something like this. In fact, this looks very similar. It looks like a reflection of what we had on the right part. Now we are going to continue from pi to 3 pi over 2. That corresponds to the blue section right here. So analyzing things, at pi, the length is exactly 1, But then those rays are getting shorter and shorter and shorter. And at 3 pi over 2, we go to 0. So we end up at the pole. So trying to mimic that, let's see, at pi, we are at 1. So at pi, we are here. And then we're going to be getting closer and closer, and eventually we will collapse at the origin exactly here at 3 pi over 2. So let's start. So here, getting shorter every time, and that's going to be tricky to capture, but we end up getting something like this. So then we have a little portion like that. And then going on to the purple, same idea, right? We're coming from 0, and the rays are now getting larger and larger, and we end up with r equals 1. So we're going to go as large as 1. So from the pole, now the rays are gaining momentum. They're getting larger and larger and larger, and 1 over here. So then you notice that you end up getting something like that. So this is now the shape of the graph. The shape of the graph goes like this, along like that, here, then it transitions into a little portion like that, and then it continues like this, right? You notice how nice over here we touch the pole. So following the motion of, if you want to follow the motion of theta, pretty much theta moved in this direction like this. It went here, and then it continues upwards. You don't have to follow the motion of theta. I'm just saying in case. So this is the shape over here, that shape. Okay, it looks like maybe like a little heart, something like that. This is why this particular shape is called a cardioid when working with polar graphs. So this is the shape of a cardioid because it looks like a heart. Example 5 is asking us to sketch the graph r equals cosine 2 theta. Again, just as before, I started with sketching r equals cosine 2 theta in the traditional sense. You can see my sinusoid here. Because we have 2 theta as part of our angle, then that means 2 complete revolutions within 2 pi. I don't care what happens after 2 pi because repetition occurs. So from 0 to pi, I have 1 cycle. From pi to 2 pi, I have another cycle. I have already broken down the graph into tiny little color segments, and we're going to follow the shape of those rays here in the polar grid. Also, I want you to notice that we are going to have some negative lengths, so we are going to have to do some reflections about the pole. We're going to have to go across the pole. So in some areas, some things are going to get a little bit messy, but then we're going to go ahead and erase them. Just try to bear with me. So sketching from 0 to pi over 4. We notice that at 0, when theta is 0, we are at maximum length of 1. This is the highest length achieved, and the lowest length will be negative 1. Then the rays are decreasing in size, and at pi over 4, we are going to be at the pole. So starting with that, we will label our polar axis. I'm going to take 4 marks to be 1 so that we get a more accurate sketch. So here we have 1, 2, 3, 4. So let's make this over here 1 so that we really see a very nice curve. Otherwise, everything is going to be cramped together and things are going to get a bit messy. All right, so when theta is equal to 0, we are right here at 1. Then when we go to pi over 4, let me circle that. Here is pi over 4. We're going to collapse to 0. So these rays are going to be getting smaller every time, and smaller, smaller, and smaller, and smaller, and then 0 right here. So I already see this shape taking place, something like that. All right, could be a circle, could be an ellipse, who knows? Now let's transition to the purple region from pi over 4 to pi over 2. So let me do that. Pi over 4, we said, to pi over 2. So here is pi over 2. And we're going from pi over 4 to pi over 2. And if you notice, those lengths are negative. We are going from practically 0 all the way to negative 1. So I will pretend right now that r is positive. If r was positive, going from 0 all the way to 1, so this is 1, 2, 3, 4, that's going to be 1, we would have tiny little rays getting bigger and bigger. Every time they will be getting bigger and bigger, just like this. And then eventually they will go to 1. So I would get a shape that looks like this. But now I have to reflect that about the origin. So 1 is going to go to negative 1. 1, 2, 3, 4. So right here. And then these guys are going, so everything that was mapped over here is going to go onto here. So then the shape will be something like this. Let me fix that a little bit more. It's going to be something like that. Okay, you can see, look at this reflection right here. So see what is happening right here reflected onto this, right? This is going to be the ray at pi over 2. So now though things are getting messy, I do not need this portion. I'm going to go ahead and erase it. Okay, so this is what I have right now. All right, so now that I have that part, we're going to go ahead and work on the blue part. Oops, sorry. Okay, so now we're going to go ahead and work on this blue part right here. Okay, I actually erased some of these rays. Okay, so now I notice that those rays are going from negative 1 all the way to 0. And that happens precisely from pi over 2 to 3 pi over 4. I'm going to do that again in blue to stay consistent. So here is pi over 2. Here is 3 pi over 4. So first I'm going to start sketching as if r is positive. So at pi over 2, we should have been at 1. So 1, 2, 3, 4. So right here. So I'm going to have a ray right there. And then I am going to start getting smaller and smaller and smaller as I get to pi over 2. So something like this, excuse me, to 3 pi over 4. At 3 pi over 4, it is going to be 0. So this is now the shape that I get. However, I am going to have to now do a reflection. Remember, we were sketching from pi over 2 to 3 pi over 4. 3 pi over 4 is this ray right here reflected onto this. So then these rays are going to be reflected in this part over here. That means that if I go ahead and do my reflection, I am going to have something like that. So I really want you to see this part across the origin maps onto this part right here. So now I can go ahead and erase this portion. I don't need it anymore. Okay, so right here. Interesting. So see what I have right now? I have something that looks elliptical over here in the bottom. And then I have this half portion over here on top. Now continuing onto the red part right here. We notice that the red part will go from 3 pi over 4 onto pi. Now the rays are coming from 0 and they're getting larger and larger and larger towards 1. But what is so nice is that these rays are positive, so we're not going to have to do any reflection whatsoever. So from 3 pi over 4 right here onto pi. So going from 0 the rays are going to start getting larger as I move towards pi. So let's say right here, they're gaining momentum. First of all, let me mark down 1. So 1, 2, 3, 4. So I have to go all the way to here. So those rays are getting larger every single time as I move towards pi. Like this, like this, like this. And at pi is going to be exactly 1. So following the shape, I'm going to get something that looks like this. Now onto the black portion from pi to 5 pi over 4. So here is pi, 5 pi over 4 is right here. And I notice that now, starting from 1, the rays are shrinking and pretty much collapsing to 0. So here is at 1 at pi, which is 1, then they're getting shorter and shorter every single time, okay, until I get to 0. So now this is going to be the shape right there. And then moving on to the pink from 5 pi over 4 to 3 pi over 2. So now we notice that from 0, we're going to go to negative 1. So we're back to negative lengths. Okay, so 5 pi over 4, here is 5 pi over 4, and then 3 pi over 2 right here. I am going to sketch this as if r was positive, but then we're going to reflect about the origin. So from 0 to 1, we are going to start drawing those rays. So here is the pole, and the rays are always originating from the pole, and they're getting larger and larger. So right here. So notice how we have traced through this portion here, but now we're going to go ahead and do the reflection. So 5 pi over 4, tracing over here, will correspond to this area right here, and 3 pi over 2 corresponds to this area right here. So we are practically then looking at this portion and this portion. Okay. So this will be reflected. Let's see, at 3 pi over 2, I'm going to go to pi over 2. 1, 2, 3, and 4. That's going to be 1. And the reflection is going to look like this. Something like that. Now, onto the orange, this part right here. That's going to go from 3 pi over 2 to 7 pi over 4. So 3 pi over 2, right here, to 7 pi over 4, right here. And again, negative. So let's see what is happening. We're going from negative 1 all the way to 0. So negative 1 to 0. Again, I will pretend that I have positive r's. So from 1, let's say, so right here on to 0. So I'm going to keep drawing those lengths like that, like that, like that, and 0. So now when I do my reflection, this portion right here is going to go onto this portion here. So I am going to have something that looks like this. And now the final gray area right here from 7 pi over 4 to 2 pi, that's going to be positive. So then I won't have to do any reflection whatsoever, and we're going from length 0 to length 1. So from 0, and we're going 7 pi over 4 to 2 pi. So 0 over here, we're going to start increasing in length as we move towards 4 pi, like that, and like that. So now I notice that I have something that looks like this. And this is my finished graph. Now, so that you can really see what we get, I'm going to trace everything in red, meaning like this, like that, like that, here, and here. Okay. How beautiful. What we get is a rose. a rose with 4 symmetric petals. I know that some of the petals look a little bit wider than others, but that's because I was not actually creating a table of values. So there is a little bit of inaccuracy. That's okay. We only wanted a sketch. So you can beautifully see over here what is happening. Now, if you follow all of these colors, you may be able to describe a path if you want to, just by following the motion of theta. So if you remember, we started with the green portion moving from 1. We moved in this direction right here. Then we went onto the purple region, so we moved in this direction. Then we went onto the blue region. This portion used to be blue. We moved like that. Then onto the red right here. Then onto the black right here. Then we went onto pink. I don't know if you can still see the pink here. Then there is a little bit of orange here. And then finally we came onto the gray. Even though you see orange, remember that this orange was negative, we ended up reflecting it here. So you can follow the motion of theta just by following those colors. So this is a rose with 4 petals. Example 6 is asking us to sketch the following curve. R equals 2 cosine theta minus 1. Just as before, we see the sinusoid sketched in the traditional sense. Theta along the horizontal axis, and R along the vertical axis. We are going to start following the motion of these radial rays. I already started drawing them, coloring them, as I've done in the previous 3 examples. So in the first section, what I did was, in order to find this value pi over 3, I practically found the x-intercepts, or in other words, the theta intercepts of this equation. I was thinking in the traditional sense. So I came and I said, when will 2 cosine theta minus 1 equals to 0? And I practically isolated cosine theta equals to 1/2, and then I solved this mini equation. I found all the values of theta that satisfied cosine theta equals to 1/2. And that's how I found pi over 3, and then everything follows nicely after pi over 3, pi over 2, pi, 3 pi over 2, 5 pi over 3, and 2 pi. So this is pre-calculus stuff. You should be able to handle that. All right, so now on to the sketching. Let's quickly analyze from 0 to pi over 3. The length of this ray when theta is equal to 0 is exactly 1. And then the rays, look at them, they're decreasing in size and they go all the way to 0 length. So we're going to be starting from 1, and then we're going to be decreasing to 0, eventually ending at the pole. Doing that, let's see, we're going to be going from 0 to pi over 3. Here is pi over 3. And I am going to let 2 marks represent 1. And I will now start sketching the rays. So when theta is equal to 2 pi, the first ray is going to have length of 1. I'm going to draw it right here. And then they're going to be decreasing in size as I move towards pi over 3. Just like that, smaller and smaller and smaller. So if you notice, I am going to have something that looks like this. Now onto the blue region right here, from pi over 3 to pi over 2. So here is pi over 3. We're going to go to pi over 2. We notice that the length are going to start coming from 0. They're going to get larger and larger, but negatively. And then we're going to go as large as -1. So I am going to be sketching as if R is positive, but then once we have the shape, we're going to go ahead and reflect it about the origin. Let's do that in blue to keep track of our colors. So now we're going to go from pi over 3 over here to pi over 2. And then again, coming from 0, tiny, tiny, but we're growing, growing, and growing towards 1. So we're going to have something that looks just like this over here, if you notice. This was from pi over 3 to pi over 2. Pi over 3 is going to lie on this opposite side over here. Pi over 2 on this opposite side right here. I would like to quickly mark that so that I don't forget. So negative 1 will be there. And then we said pi over 3 is going to be somewhere here. All right, so now onto the reflection. In other words, this tiny section will fall into this region over here. So we're going to go like this, following the curve, just like that. Now what I am going to do is to erase the portion that I don't need. So this portion right here, let's erase it. Okay, I'm just going to try to keep the green and the blue. Okay, so again, this is the portion that I just developed right there. And here is the green one. Okay, all right. The pole, I'm losing the pole. Let me keep it in black there. Now we're going to go onto the red part. I noticed that the red goes from pi over 2 all the way to pi, still negative. And we're going from negative 1 all the way to negative 3. I will mark 3 units here at pi, 1, 2, and 3. And again, I am going to be first sketching my rays over here as if they were positive, and then we're going to go ahead and do the reflection. Now we're going from pi over 2 right here all the way to pi, and we're going to be going from as we said, from 1 right here all the way to 3. All right, so that's going to be interesting. So let's go. We are going to go, we're going to be here. Then we're going to be gradually increasing. Okay, just getting larger, 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 larger here, larger, as I'm getting closer and closer to pi, and then finally here. So if this was perfect, you will see you're going to have a tiny motion, a round motion like that. Okay, so from here, something like this. So now doing the reflection, remember, this has to go down in the opposite direction. That means that we are going to go here, and then let's see, this pi is going to go across. So practically this region will be reflected onto here. So that means that we're going to have again 1, 2, and 3. And then we should be able to continue that motion like that, something like this. Now I am going to go ahead and erase a lot of this. I don't need this anymore. It's just confusing. Okay. All right, so that's what we have. Now we're going to go on to the gray part. The gray part still negative, now from pi to 3 pi over 2. And those rays are starting at negative 3. They're getting smaller and smaller, and then they're going to go up to negative 1. So in the same way, I am going to start sketching them as if they were positive. From pi to 3 pi over 2. So here is pi, here is 3 pi over 2. Let me also, before I begin, erase this blue part here. Okay, So we said from 3, imagine the ray right here, we're going to be going all the way to 1. So where is 1? 1 is right here. So we're going to be getting smaller, just like that. Remember, this is just a rough sketch. It can never be perfect. Like this, like that, like that, like that, and eventually here. So we end up getting something that looks like that. But now the reflection. These rays are going to be reflected onto this region right here. The region that is going to go from 0 all the way to pi over 2. So doing that reflection, this one is going to go here. This one is going to go to 1 right here. So that's going to be something that looks quite symmetric here. So now let me erase this part. Don't need it. I will also retrace the blue section that pretty much was lost because of the gray. So here it is. That's what I have so far. Okay, now we're going to go and do this black portion from 3 pi over 2 to 5 pi over 3. That's going to be in black. 3 pi over 2, 5 pi over 3. It is still negative. So I am going to do it as if r was positive. I notice that we are now going from -1 all the way to 0. So I'm going to do as if I'm going from 1 to 0. So at 3 pi over 2, I am here. Then these rays are going to be getting smaller and smaller and smaller and smaller. So practically what I have is something that's too large, something that looks like this. So now doing that reflection, that was between these two radial lines. So now that's going to go between these two radial lines over here. So then the reflection is going to look just like that. Okay, and if you hopefully you can see that reflection going on. I'm going to go ahead now, and just as before, I will erase this part. I don't need it. All right, so there should be a connection here, a nice connection here. So now that I have that, I now have to do the last portion here in purple. So I noticed that that portion goes from 5 pi over 3 to 2 pi. The length of the rays go from 0 all the way to 1. So let me do that. 5 pi over 3 to 2 pi. And those are positive lengths, so that's going to be nice. We're going to go from 0 over here, and they will start getting larger and larger up to 1. So they're going to go like this, like this, like this, and like this. So you notice that we're going to get this portion right here. So now let's put everything together. Let me choose a color that we haven't used yet to do that. I'm going to choose orange, and I'm going to trace through the entire graph so that you really see the curve all together. So then the curve goes like this. Like that. And like this. So this is the actual shape, something that has a little loop inside, and then a loop curves on the outside nicely. So we see an inner loop. The name of this shape is actually called limazon, something like this. So this is your typical limazon in polar coordinates. How lovely. Again, if you wanted to track down the motion of the angle, remember that we went, and you can even use the Cartesian here, just follow the colors. we went green, then blue, then red, then gray. I think that was the gray part. And then we did black over here. And then finally, we did purple. So we went like this, from 1 towards the left, like that, across, and like this. How lovely. I want to end this section by revisiting the discussion that was initiated in example 2. If you remember there, we were talking about lines. I'm going to go ahead to the Cartesian plane, right here. This is the x-axis, this is the y-axis. And the line that we were looking in example 2 was a line that passes through the origin. In this case, we said that in polar form, if we have a line passing through the origin and we want to represent that line in polar form, we can do so by just specifying the value of theta that is formed from the positive x-axis. And if you remember, we can think of the positive x-axis as the polar axis. In fact, I'm going to go ahead and draw it over here in green. Imagine that I'm thinking of this as my polar axis. So when I measure this angle right here, theta, then I can represent this line right here as theta equals whatever the measure of that angle happens to be. I believe that in example 2, it was theta equals 4. I don't remember, but it was just a constant. Theta equals 4. Let's pretend. Well, in this case, based on the way that I drew it, it seems to be more halfway through. So let's say theta equals 1. Why not? So, and just to clarify, when I say 1, I mean 1 radian. So a point on this line, and I'm thinking in terms of polar coordinates, points on that line are expressed in the form r, comma, 1. Again, knowing that theta is equal to 1. So practically I can put any particular length, any length. R is irrelevant. R can be 1, R can be 2, R can be 3.5, R can be negative 2.5. The point is that we're keeping the angle fixed. The angle is not changing. What changes is R. R is constantly changing. And that's how you're getting that line. If R is 1, you're somewhere here. If R is 2, if R is 3. If R is negative 1, you're below. If R is negative 2. And as long as we keep theta fixed, then you end up getting a beautiful line. So this is why in polar form, every time that we are in polar form, the equation of a line that passes through the origin is written down or is expressed as theta equals c radians, right? This is the measure of the angle, and that angle happens to be fixed. But what if I have a line in the xy plane, in the Cartesian plane, that doesn't pass through the origin? Can I find its polar equation? Here on the right, taking you back over here, if I am in the Cartesian plane and I have a line that passes through the origin, I know how to represent it in polar form. In polar form, it will be equal to theta equals c, where theta is the measure of the angle that is formed by the line and the positive x-axis. However, here on the left, I have a blue line in the Cartesian plane that is not passing through the origin. Is there a way for me to find its polar representation? The answer to that question obviously is yes. There will be a way to do that. In order to find the polar representation, you will need to know 2 points on this line. The first point is just completely random. a point on the line, just a point. You're going to have to know its distance from the origin, because that will relate to r. I still want you to imagine that we have the polar axis over here sitting on top of the x-axis. It never hurts to keep that in the back of your mind. So if we choose a random point on this line, we're going to have to know r, and we're going to have to know theta, right? And that's not difficult to figure out. But you will have to know another point. That point is going to be on the line, and is going to be the point that is closest to the origin. In this case, the point that is closest to the origin is going to be right here, somewhere here. In order to find it more carefully, I am going to draw a segment. I'm going to intersect my blue line, but in order to find the closest point, that intersection has to be at a 90-degree angle. So then the point that I want is this one right here. We are going to denote this length over here by, let's say, D, and the angle that is formed by that perpendicular segment, we're going to call it alpha. Why not? So then in polar coordinates, the coordinates of this point are going to be D for the length, alpha for the angle. So here are the 2 points that we need to work with. A random point on that line in polar coordinates. And then we need the point on the line that is closest to the origin, again in polar coordinates. Such a point has to fall on this segment, but this pink segment has to be perpendicular to the line. This point is the closest point to the origin, the point on that line. So now if you noticed, we have formed a right triangle. I'm going to go ahead and highlight that triangle, or actually trace it in red so that we really see it right there. And what I want is this angle inside. Well, that angle is easy to find. That angle is going to be alpha minus theta, right? And now I can use right triangle trig to find the polar equation. So here is r, right there, right? So right here you see r, this length is d, and the angle between r and d is alpha minus theta. So I think that because r is the hypotenuse of that right triangle, and D over here is the adjacent side, and I am thinking of the origin as the angle in question, where everything is going to be measured from, then I'm thinking of cosine. I know that cosine of alpha minus theta, so cosine of alpha minus theta, the angle inside of the triangle, is going to be equal to the adjacent over the hypotenuse. So D divided by R. I'm going to put this over 1, and I will now cross multiply. So then that is going to be R times cosine of alpha minus theta equals to D. I'm going to solve for R. R is equal to D over cosine of alpha minus theta. Let me continue over here. I need more space. So then R is going to be, now instead of having a fraction 1 over cosine, I know that 1 over cosine is secant. So D times the secant of alpha minus theta. And in general, the variable here is really theta, because this was the random point. If you remember, d comma alpha was a specific point. The variant point, the point that we just randomly chose, could have been any point on the line, was point P, r comma theta. So I want you to think of theta as playing the role of x in the Cartesian plane. Theta is your variable. So in general, it is the norm for theta to appear first. So I can always do that. I can write d times the secant. I can factor a negative out, theta minus alpha. And I know that because cosine is an even function, then secant is even. So this negative right here, this negative here, practically disappears. So r is going to be equal to d times the secant of theta minus alpha. And we found the polar, oops, too big. We found the polar representation of the line. There it is. So from now on, we know that this is the polar equation of a line on the Cartesian plane that doesn't pass through the origin. It doesn't have to pass through the origin. If it passes through the origin, we know that it is going to be theta equals to c. If it doesn't pass through the origin, not a big deal. It is going to be d times secant of theta minus alpha, where you are going to have to know d, however. You're going to have to know exactly the coordinates of the point on the line that is closest to the origin. So we will have to know d comma alpha. Somehow we're going to have to figure that out. Sometimes it is going to be given to us, sometimes it will not be given to us, and we're going to have to figure out d, and we're going to have to figure out alpha. I'm going to do an example to show you how to do that when we may have to explore a little bit deeper. As the last example here, I have a situation where we are given 2 points, negative 4, comma 0, and 0, comma 4, and we are told that a line is going to pass through those 2 points. We're being asked to write the polar equation of the line passing through these 2 points. Here I already drew the line passing through the point 0, comma 4 and negative 4, comma 0. This line doesn't pass through the origin. That means that we're going to use the form of the polar equation that we just developed. In polar form, the equation of this line should be r equals d times secant of theta minus alpha. I want you to remember that theta is like your variable. So what I need to figure out pretty much is d and alpha. D and alpha came from the point whose polar coordinates were d comma alpha. This was the point on the line closest to the origin. In order to find that point, remember, you go from the origin perpendicular to the line, something like this. And right here is where we should have that point. Now, this angle here becomes alpha, and this length over here becomes d. So that's what I need to find. I need to find alpha, and I need to find d. Once I find alpha and d, I have nicely the polar equation of my green line. So how do I find d? How do I find alpha? There could be many ways of doing that. I'm going to go ahead and do it from straight geometry. First, I'm going to figure out the slope of this line. So using my delta y over delta x, we're going to have 4 minus 0 over 0 plus 4. That is going to give us 1. So if the slope of my green line happens to be 1, the slope of the pink segment is going to be negative 1. And I know that because those two lines are going to be perpendicular. So then I know that the slope of the pink line, let me even write it in pink, is going to be equal to -1. Now, what is the slope of, what is the equation of the green line? So the equation over here of this line. So let's see, we are going to use y equals mx plus b, y equals x. We know the y-intercept. The y-intercept is the point 0, 4. That means that b is 4. So this line has equation y equals x plus 4. Now the pink line, this one right here, is going to have equation y equals -x. And this is because the slope is -1 and it passes through the origin. So b has to be equal to 0. And I want to know the point of intersection. So then, to figure out the point of intersection, I'm going to go ahead, take the pink line, take the green line, and set them equal to each other. So when will x plus 4 equals to -x? When 2x equals to -4? So when x is equal to -2. And right away, I know the Cartesian coordinates of my pink point right here. The Cartesian coordinates are going to be -2, 2. Again, remember the pink line or segment passes through the origin at a 45-degree angle. That's because the slope is -1. So if x is -2, I know that y is going to be +2. Easy to figure that out. So now I know x, I know y, so I can figure out alpha. In order to figure alpha, I am going to use tangent. Why not? I know that the tangent of alpha has to be equal to -2/2. That means -1. The easiest value for alpha will be -π/4, but I want the alpha in the second quadrant. So then my true alpha will be π/2 plus π/4. So then that's going to be common denominator 4. So that's going to be 2π over here plus pi. That will give us 3π/4. And that's how I find my true alpha, the one that I want. So I already know that this alpha right here, this angle right here, is going to be 3π/4. Now what I need is d. I have to find this distance right here. So in order to find this distance, can we just use the distance formula? I'm hoping that you remember from your studies in algebra, and if not, you can quickly search it up, that the distance between 2 points in the Cartesian plane is given by this formula. Distance equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. And this is whenever you are given 2 points, x1, y1 on a line, and you are given x2, y2 on that same line. Here the points that I have are -2, 2, and the origin 0, 0. So in order to find that distance, I'm just going to go ahead and plug in those values. So we're going to have -2 minus 0 squared plus 2 minus 0 squared. In both cases, that's going to give me 2 squared, which is 4, plus 4. Let me continue here. So d is going to be equal to the square root of 8, which is going to be 2 root 2. So practically then I found everything. D is equal to 2 root 2, and I know that alpha is equal to 3 pi over 4. So conclusion, the polar equation will be R equals 2 root 2 times secant of theta minus 3 pi over 4. Okay, so I'm going to go ahead, box it up, and that's the equation of this line in polar form.